Okay, so for today's deep dive, we're jumping into one of the biggest bottlenecks for high-performing language models, context length.
Right. When you give an LLM a really long document, we're talking 100,000 tokens or more, the cost just goes through the roof.
And we got a fascinating paper here that tackles this head-on. It's called End-to-End Test Time Training, or TTTE2E.
And that cost escalation, that's really the central conflict. I mean, today's best models, the transformers, they're built for almost perfect lossless recall. To do that, they use full attention.
And that's where the problem is.
Exactly. You double the document length, and the computation required, it quadruples. That quadratic cost is why long context has always been so hard to do efficiently.
This is where the paper makes a really crucial pivot. They don't see it as an architecture problem to be solved. They frame it as a continual learning challenge. They use this great analogy, that humans don't recall every single detail perfectly. We compress experience into intuition.
And that's what TTTE2E tries to make the model do, compress the context right into its weights.
So how does that actually work in practice? I mean, how do you get a model to build intuition?
Well, they start with a pretty standard architecture, a transformer, but it uses sliding window attention, or SWA.
Okay, and for anyone who doesn't know, SWA just looks at a local window of tokens, right? Maybe the last 8,000 or so.
Yeah.
To limit that quadratic cost.
Precisely. But that creates a new problem.
You lose the global context. That's the trade-off. So how do they get that long-range understanding back?
By forcing it to keep learning. Right at test time.
During inference.
Yes, that's what they call the inner loop. As the model is reading the text, it's constantly predicting the next token, and it uses the loss from that prediction to immediately update its own weight.
So it's actively writing the long-term context into its own memory, its parameters as it goes.
You got it. It's bypassing the short-term limits of the sliding window.
That sounds like it would be incredibly slow during inference, though. Aren't you just moving the computational cost from one place to another?
You would think so, but that's where the end-to-end part is so clever. There's an outer loop that happens during the initial training. They use meta-learning to basically optimize the model's starting weights to be a super efficient student for this test time process.
So you're pre-training the model on how to learn quickly from a new document.
Exactly. And to keep it fast, they're really smart about what they update.
Right. The paper mentioned they only update the MLP layers and only in the last quarter of the model?
Yep. They freeze the heavy attention and embedding layers. The MLP layers are where knowledge is stored most densely, so updating them gives you the biggest bang for your buck in terms of memory compression without the prohibitive cost.
Which leads to what seems like the holy grail here, performance that scales but with a constant cost.
That's the big result. Looking at their graphs, TTTE2E's performance, its test loss, it scales with context length up to 128K tokens in almost the exact same way as a full attention transformer.
And other constant cost methods like Mamba or gated delta-net, they just can't keep up. Their performance drops off in those longer contexts.
They really do. And on top of that, TTTETE gets constant inference latency, sort of like an old RNN. The paper says it's about 2.7 times faster than full attention at 128K context.
What's really fascinating to me is where that performance gain comes from. It's not what I expected.
Go on.
It actually performs better than full attention, and the advantage mostly comes from the earlier tokens in the sequence.
Right. Because its weights are so focused on the immediate task, the present mini-batch. A static model with full attention has to kind of, prepare its weights for all possible futures at once, which is a much harder learning task.
Okay, but there has to be a catch. There's always a trade-off.
There is, and it's a classic one. This kind of compression is lossy.
So tasks like needle in a haystack, where you need perfect specific recall.
It has a definite Achilles heel there. Full attention still blows everything else out of the water on those retrieval tasks.
Yes.
You're absolutely trading perfect memory for this massive gain in speed and efficiency.
So in the end, they've basically engineered a memory hierarchy. You have the SWA for short-term, in-the-moment memory.
And then the updated weights become this dense, compressed, long-term memory. It's a really elegant balance.
It really is. And it leaves you with a pretty provocative thought to wrap up on. If TTTE2E is already showing an advantage over full attention on those early tokens, before the test time training has even really kicked in, what does that say about the power of meta-learning for just model initialization, about just learning to learn?
It suggests that initial training gives the model a fundamentally better starting point. That it might have an edge even when it's just processing short sequences, something to chew on.